continue with the end, but maybe just short. I wanted to say some short things before it, how short we will see, but this is some kind of semi geometric. Semi is not clear. Why? Because it's not the full thing, it's geometric manipulation. To study shuffle algebra and also this, I will explain, because of, we will be interested in different shuffle algebra, but mainly because of restrictions over time, our main object will be shuffle algebra with the function lambda is 1 to 2 equals to 1 when Q1 to 2, Q1 minus Q2 equals 1 minus Q3 over Q1 minus Q2 cube. And one reason is why such special algebra is more interesting than others, and Q1 to 2, Q3 equal to 1 also. It was related with this real transition property, and well, in a shuffle algebra, the structure of algebra is A. Is A0 plus A1 plus A2 plus so on, and the structure of product I explained, and each spaces which we have here are symmetric, but symmetric maybe, but Laurent polynomials may be not polynomials, maybe some poles somewhere, but not far from Laurent polynomials. And if you want to prove geometrically such construction, then how? That first of all, we know that if you take symmetric polynomials, just usual Laurent polynomials, and the inverse, then such rings can be understood as equivariant cosmology of a point with respect to the group Gldg. And this is really the reason how it connects with geometry, but equivariant cosmology is really correct language for that, but for me, maybe it's too much to explain about it and introduce really what is going on, but at least partly of this story, it is possible to explain more easily, and let us do it. So first of all, we are talking about Laurent polynomials, but in algebra we have symmetric Laurent polynomials, and such things can be understood how. We can take the group Gldg C, and we can consider the Bldg ring of finite dimensional representation. And well, so if you take Gldg C and if you take finite dimensional representation, then for this finite dimensional representation it has a character, and the character is some symmetric polynomial, and representations give us actually a basis in this space, and it is it's Laurent polynomial, but up to that it is basis from Schur polynomial. And this is just yes, and in a structure of this shuffle algebra, what naively we have. So again, in this case, we have here not symmetric polynomials, but as I explained, the object in my algebra were things like this. And here the product of the I minus the j squared. And up to this point, it is the same things. But for example, as I also said, that if the function lambda is simpler, if function lambda is z1, z2, it is z1 minus q, z2 over z1 minus z2, then in this case, algebra all is similar, product is similar, but En is just such space, but without this factor. So for this case, we are just living in something like here. So it means that in this case, no, because the product is product, so it means that I have on the space the sum, and now I interpret these Laurent polynomials as a Bldg ring, or maybe let us denote it by Rn. Rn is a ring of finite space.
The ratios are where Q in your field. You have a ring of polynomials about Q.
Yes, but Q is, let us put on a simple minded point of view, Q is just parameter, just number.
Yeah, but the ring of polynomials doesn't depend on Q.
No, it does not. In all what I said, that product is product. I have two symmetric things and calculate the product. What really depends in structure of this function, Q and so on, first of all, pull here because of this. And also more subtle things about these will conditions, because it is also Q related with the will condition, but at least what? If I consider only this simplest possible case, then algebra is the sum of Rn. Each Rn is ring, a Bldg ring of representation of Jn, which I can identify with symmetric polynomials. And because we have such kind of product, so it means that we have Rn times Rm to Rn plus m, and this product surely depending in Q. And now the question is what it is. And this is a simple situation, and it is not very complicated to answer, and let me say the following things. This kind of construction always appear if we construct Bldg-like algebra and things like that, and it is calling induction and restriction business. But I want to talk only about induction, and so what does it mean? It means that naively it means that such construction is working how? That I take some representation of JLN, maybe P1, it is representation of JLN. I take representation of JLN. And then I want to construct something related with JLN plus M. Sometimes it can be also a representation, or at least it's a linear combination of some representation. Product is here P1. It means it is from the point of the algebra, it is the character of a representation in some symmetric polynomial. And here it is the character of two also symmetric polynomial, and the product is symmetric polynomial in n variable, and how to understand what is this from the point of view of JLN plus n. And how it is usually doing. It is very natural, and first of all, without AQ, how we can proceed? Let us, we have JA n plus m. And in JN plus m, we have parabolic subgroup n. This parabolic subgroup is such that the quotient Jn plus m over p n plus m is isomorphic to Grassmannian manifold of n-dimensional subspaces into n plus m dimensional space, or n-dimensional space. Anyway, it is a subgroup, and so the situation when we make calculate induced representation, in principle, it is working by the which way? I take P n plus m, and because P n plus m is subgroup like this with 0 here, then we have a map to JN plus JN. Then it means that P1 standard P2 is the representation, this guy is the representation of this. And it is always so, if I have subgroup and representation of subgroup, then I want in principle induce and construct representation of JN plus m. No, and it is good if we are working with finite group, but here it is Lie group, but nevertheless it is possible to do how? What is possible to do? So if we have representation of this group in this representation, so by this way I can construct the vector bundle on this Grassmannian homogeneous vector bundle with fiber phi1 times phi2. So what does it mean? It means that I have this Grassmannian manifold, and parabolic group is fixed point subgroup of some point, and so in each point of my Grassmannian manifold, I have a fiber which is like this. Yes, and after that, I have a bundle over this, and this is homogeneous, and so I can take either, no, if we are taking induced representation, we want to take sections. But in all cases, better to take not section, but equivalent error characteristic. Or this induced representation, and it will be something which in general is virtual representation, and it has some character. And this construction is rather simple, and take character of this and character of this. and give you the character of N plus n. Well, and what precisely this, what kind of structure we get by this way on the sum of Rn, this is the problem for students. So anyway, what is more or less evident? More or less evident that by this way we get some associative product on the sum of Rn. But the question, what is it? But in some sense, I will give an answer in a few minutes, but this construction does not depend in Q. If we want dependencies in Q, that is, we need to do the following. Let us consider if I have algebra Gln, then I can go and if I have commutative ring or supercommutative ring, I can consider the algebra Gln times A, which is usually calling the current algebra. So this is just the algebra of M times N matrices. Matrix elements are from A. And A, in principle, can be any commutative or supercommutative ring. And even associative ring is also in this case. But we need, for this example, A is Grassmannian algebra in one variable. Yes, yes, there is a Grassmannian algebra, and we can consider the corresponding to this superalgebra. Gln plus psi Gln, and it is super in what sense? It means that this is even part, this is the fourth part, and all brackets are clear what is this. The brackets here are 0, and this acting on this is just a joint action. Yes, and no, we can consider now the category of graded representations of this the algebra, the superalgebra. And no, in principle, what is going on? No, I skip some details, but the situation is clear. I consider bigger algebra, but if I'm talking about finite dimensional representation, and if I'm talking about irreducible representation, that irreducible representation, this Lie algebra has the same as Gln. Yes, and so no, I want a representation which integrates to a finite dimensional representation of corresponding group, and if we restrict ourselves by this representation, that Grothendieck ring doesn't change much. Grothendieck ring will be more or less the same Rn. No, the standard difference is that we have additional grading. So, because now it is better to understand this as graded algebra. And so up to this, it is the same thing, but representation now is finite dimensional representation of Bldg, and this part is acting by zero, and also some gradient there. Now, no, forget about grading, and it is up to this, it's just the same thing. Now I want to use the same construction of induced representations, and so, but induced representation, it means what? Now we have super the algebra like this, and we have corresponding super the group, and also anyway, so I have group Jn, but now let us put some symbol here. It is super group, but it is over psi. It is bad notation, but maybe it will be like this. And here we have again parabolic subgroup, also dependent in psi. Well, and nothing really changing, but because before it was Lie algebra, for example, matrix elements were numbers, but now they are elements from this Grassmannian algebra, and here we can play with such objects just by the same way as we did in the usual situation. For example, we can take a quotient, this by this, Jn psi over p and m over psi. Yes, and what is changing? Without psi, we got just Grassmannian manifold, as I said, and now we have this Grassmannian manifold with psi, and it has to be some super manifold. And what is this super manifold is also very, very clear what it is. It will be a cotangent, tangent bundle. I think so. Tangent or cotangent? I think tangent. Right now, I think as a super. If wrong, we will see it in a moment. But right now, I think that it will be tangent bundle of Grassmannian manifold. In any case, if I have manifold and I have a vector bundle over it, in this case, it's bundle supposed to be tangent, then I can construct the super manifold, just saying that this bundle is related with all odd coordinates. And now the construction is this induction business. What is going on? Again, I take parabolic group M. Now it's depending in psi, and it has a map to usual Jn times Jn without psi even, and I have finite dimensional representation and that tensor product. And so by this way, I can construct the vector bundle over this thing. And now the definition of a product is equivariant Euler characteristic of the corresponding bundle here. But I said that I understand this algebra as a graded algebra, and this has grading 0, it has grading 1. And this is super manifold, and so it is what? It is Grassmannian manifold, but in each point I have fiber tangent space. Yes, and but this manifold, because no grading is grading, because this T fiber in this point is related with this part of my D algebra, so it has grading 1 from this point of view. And so people usually saying that in a way that this manifold has additional grading. So it is some one-dimensional torus is acting here, and on a fiber it is acting by dilatation, just this way. And so now if you determine product now, then you are going by the standard way. You take this in constant bundle here, and you calculate the equivariant Euler characteristic, but as a graded manifold. Yes, and therefore you get some graded. As a result, this Euler characteristic will be virtual representation, graded, and we can calculate the Poincare polynomial of this, and it will be the result of our product. So I take P1 and P2, then I make up something on this manifold, and then I consider this equivariant Euler characteristic, and this is it. And now, what is more or less evident? This, because I take this Poincare polynomials, so well, result is some graded space, and for graded space I calculate Poincare polynomial, I get something depending on Q. Q is Poincare polynomial, yes, and then this Q I now understand as a parameter. Therefore, we get some algebra with some product, and now this product depending on this Q. Now the question is how to calculate this product, and this is easy, also more or less, because if you calculate this equivariant Euler characteristic, how it is doing on a flag manifold or a Grassmannian, we use Lefschetz fixed point formula. If you calculate equivariant Euler characteristic, what you do? You have this Grassmannian manifold, and you need to calculate their equivariant character. And this equivariant character, Lefschetz fixed formula says that if you take some manifold, super or not, it doesn't matter, where some torus is acting, and you have fixed number of fixed points, and if you calculate the equivariant Euler characteristic, it will be the sum over fixed points, and term the corresponding of fixed point is easily calculated, and I say something about in a moment, but I want to say that now statement this calculation, if you really calculate the character using left fixed point formula, then as a result, no, in principle, what we expect, I have character of this, it is f. I have character of this, it is g. And as a result, it has to be symmetric polynomial in n plus m variables depending in q. And the statement is that Lefschetz fixed formula gives us precisely the shuffle product in this special simple case. And well, no, to see it, I need to explain how to calculate what is Lefschetz fixed formula. I do not want to do it, but I want to do what? That the structure of the product is what? It is f. Again, let me write C1 and so on, Zn plus m is equal to f C1 Zn times g Zn plus 1 Zn plus m, and here we have a product. Product is z I minus q z beta. Here we have z I minus z beta alpha. Alpha from this group and beta from this group. And here symmetrization. Now, first of all, because this function is symmetric and this function is symmetric, really this symmetrization is going on over the number of terms, real different terms in this symmetrization is n plus m factorials over n factorials over m factorials. And this is full symmetrization, but this is because they are symmetric. So the sum contains so many terms. Now each term here is corresponding, if you have usual Grassmannian of n-dimensional planes in n plus m-dimensional space, then the number of fixed points is just this, just binomial number. And Lefschetz fixed structure of the Lefschetz fixed formula is usually the following. So what we have, if we have manifold, if I have fixed point, that contribution of fixed point is what? First of all, character of a fiber on this point, it is this. If we have just first fixed point. And also, in Lefschetz fixed formula, we have a character of a space in usual case, in a space of functions of formal series in the vicinity of this point. And if we have just Lefschetz fixed formula for Grassmannian, then we have not this term, and this term corresponding to a character of function in a small vicinity of a point. But because we are working with supermanifold, we have additional bundle, and this additional bundle take care of this part. And Q here just appear in the correct place because we just count the degree of this. So this formula is just it. Now, No, this is maybe all what I wanted to say about this, but I promised to explain this function by the similar manner, and let me do it. This is not complicated. Suppose we are talking in the case we do the same things, but we are talking about product to Grassmannian algebra in two variables. Now, if I do this, and in principle, I'm explaining to you that it is theoretically with some complications. We can take any ring there, and it's possible to do. But look here. Again, that in such situations, up to again some complications. In principle, I also want to have a product Rn where n plus m, and now this algebra has two gradings, one in Xi1 and second for Xi2. And because of this, we expect a product here depending in two grades. And what I want to say is that really we get almost get this object, but at least here all depending in two variables, Q1, Q2, but Q3 is related by this. But how it appears in this situation? Well, now contribution, in this case, contribution of a fixed point will be the following. We still have a product of the alpha minus the beta, and this is because our point is the point of a Grassmannian, and this part describes the function in the small vicinity of a point. No, because the better to understand it is 1 minus the beta over the alpha, and this the beta over the alpha just coordinate in the vicinity of a fixed point. There. Yes, and this is it. But now, because it is a Grassmannian algebra of such sort, that situation will be forming. That our supermanifold will be like this. It will be Grassmannian, but we have not one tangent boundary, but two. One related with Xi1, second with Xi2. And both of them will be odd. But we also have something related with Xi1 and Xi2. And this will be even part. So this super manifold, it is looking like this. Or odd, the even part of this Grassmannian plus contribution of this, and the odd part is this. And if you just formally and naively write down the contribution of a point, you will have what? Here we'll have this. On the top, you will have the alpha minus Q1. And this Q1 and Q2, they count grading. One of Xi1 and second of Xi2. But we have additional part which is corresponding to this. And so we have here the product of the alpha minus Q1, Q2, Q no, here definitely is one problem that it is a rational function, but we expect in principle here Laurent polynomials naively, but forget about this. I want to put it under the carpet, but up to this, it is a product with such functions. And actually, this function is the same as this. I explained that if you forget about this business and just describing the shuffle algebra, that if you have shuffle algebra, this function lambda C1, C2, and if you have shuffle algebra with function C1 times mu C1, C2, where this function is symmetric, then the corresponding shuffle product basically is just the same. No, how much it has to be saying maybe a little bit more precise, but suppose lambda is 1. It means that if you take here just symmetric function, then, no, first of all, it is evident that if you take symmetric function here, and lambda is 1, and write down the formula for product and shuffle algebra, that it gives you commutative algebra, so basically it will be the same. And if you replace lambda to this, that algebra will be the same after some simple gauge transformation, just a simple changing of value. Anyway, if you believe me that what we get with this function is the same as what we get, we can, if we have this freedom, product of this function to something symmetric, then what we can do? First of all, we can put here symmetric function is z alpha minus q1, q2, z beta times z alpha minus q1, q2 inverse. Z beta I can put it in the top. After that, cancel this. And here I have the alpha minus the beta, but up to symmetric function, which is the same as q here. And so you see that I have here q1, q2, and here q1, q2 inverse. And this is just what I promised you here. We get this condition. Again, it is some no, it is good point of view, but it is surely not enough. And for example, later I explained that such kind of algebra, it is something what is acting on the equivariant cosmology of Gilbert schema or Giesecke schema, something like that. And so this approach is related with this by the following way: that here we have Grassmannian algebra, but if we consider the dual object taking this x1, x2, and looking the Gilbert scheme for this, and in some way it's related with what I'm talking. And no, this is not a very precise statement, sure, but it has some meaning. And it's one thing. And other things which is also interesting, and maybe only now I can mention it, that you can ask me, suppose I want to consider the object like this. It will be a Grassmannian algebra, for example. But suppose I want psi1, psi2 equal 0. And it is just, no, in principle I can put here any algebra and just trying, and I can repeat all this business, why not? for example, I can take this. So it means here it will be constant plus psi1 plus psi2. Yes, and then what kind of, from the point of a shuffle, it means that we have not this Q3, so we have not this term which relates with psi1 times psi2. And it is interesting, and maybe it has to be some reason for this, that corresponding shuffle algebra from the point of modular space is related what people are calling non-commutative Gilbert scheme. So it means that this is the ring of finite dimensional, modular space of finite dimensional representation of free algebra. And the algebra which is acting here is this. Okay. Anyway, what I explained, I did it longer than I wanted, but nevertheless, maybe it has some reason because I explained that this is the object which is interesting to deal with, and it is important, and so on. Yes. Now, let me go. And by the way, and so such kind of such point of view give you a sort of explanation where we can see this shuffle product. But if you ask me the role of will conditions there, then it is no something I can say, but really I do not understand very well what is going on and how to see this will condition geometrically or in some understandable way. I think it is not known. Yes. But, and again, maybe it is not good to say about this now, but suppose you are knowing this and thinking about shuffle algebra by this way. And, well, I explained to you the situation with 1 and with 2. And you can ask me why not 3. The answer is yes, and it is surely nice algebra. But first of all, no, we have, no, in this case we have shuffle algebra because if you can make out this Grassmannian business, we get that. But unfortunately, a lot of terms in the top and a lot of terms on the bottom. But nevertheless, it will be algebra with shuffle, multiplication, and so on. And it is definitely connected by some way with what is people doing with three-dimensional Gilbert scheme. No, our answer is definitely yes, but the situation is completely unclear. So if you even try to compare some algebraic information with some known things from that business, that complete confusion. So no, it is just because the subject is very mysterious and different. And now, well, stop about all this. And now, let us return to this algebra. So we have shuffle algebra, and this shuffle algebra is what? That let me just repeat what we want to instead. This is E0 plus E1 plus E2 plus so on. And then AI, AN is the space of polynomials, C1, Cn. Here we have the product EI minus EJ squared. Yes, and this function have to satisfy Will condition, and this Will condition follows from relation Q1 to Q3 to Q1. And I said it, but let me repeat. That what we actually studied, P have to be 0, if Z1, Z2 over Z1 is Q1, and Z3 over Z2 is Q2, or Z2 over Z1 is Q3, and Z3 over Z2 is Q1. And they are related with the wheel like this. For Q2, Q1, and Q3. No, in principle, you can ask what's happening if we consider more complicated wheel, and it looks like that we can do it, but all such the wheel, they follow from this. Therefore, what is it is the definition, and this definition will work. So our shuffled algebra is just consists in functions which are satisfying such condition, and at least what is evident that or clear from what I explained yesterday, that star product preserve this 0 condition. And no, to understand something about this algebra, let me say, and I want to continue at the very end of my lecture, but I want to be short. And no, before that.
In this case, P and lambda is the same.
What?
You mean that in P, that condition is the same as the condition of the lambda is 0 on the left-hand side? No?
Yes, it's no, this condition and condition that lambda are 0 somewhere just the same. No, because lambda, this, it's 0, is this, so it is it. No, maybe before the discussion about precise things, how to just algebraically looking to this. Well, in principle, because of geometry or because of this Will condition, we like these things. But in principle, why not to ask the question? Suppose Q1, Q2, Q3 are generic. Then it is possible to prove that, in this case, it is possible to prove the following theorem. Unfortunately, it cannot be exercised for students because not very complicated, but it needs hard work. The statement is that in this case, algebra with a shuffle product is with shuffle product is generated by A1.
So in this case, what you want to say is that it should be rational number.
So what does it mean? It means that I take elements for A1 and start to calculate the product by linear combination of product. I get all functions, symmetric functions in the top, and this poles on the tail. Yes, and if Q1, Q2, Q3 is generic, then A1 is generate all. Yes, and when will condition in principle appear? Will condition appear if Q1 sum A, Q2 B, Q3 C is equal to 1. If something like this is true, that because of similar reason we have will condition, where A, B, C are just some integer, non-negative integer. Yes, and in this case, if it is like this, I can write Q1, Q2, Q3, and so on, like this, and it will be real. So the state theorem says for generic, it is generated by A1, and what we see is that if they are not generic in this sense, so they satisfy such relation, and this relation people, because of evident reason, they call resonance condition. If they are in a resonance, or it is, if we had when we had one Q, we had on such resonance condition Q power n equal 1. But now we have several Qs, and so it is some resonance condition, and well, in this case, starting with A1, we can get only functions which are 0 on the wheels. So we cannot get all in this case. So, and after that, there, just from the point of view of pure algebra, we have some very natural questions, and unfortunately, no answers. That first of all, generic it means generic. Generic it means that if you make a calculation over the field of rational function over Q1, Q2, Q3. But this theorem is false in this case because of this will condition. But suppose that you take Q1, Q2, Q3, which do not satisfy any condition like this. So no will relation. Is it true that generic means that no such relations are whole? It's plausible. But if it, no, the fact is, if it is true, it's more clear how to prove it. But I cannot believe that this is true. So, yes, but anyway, the question is interesting. And also the question is that opposite question is following. That suppose you have Q1, Q2, Q3, and which satisfy will conditions, then is it true that algebral functions which are zero on the wheel generate by A1 in this case? Now, for example, this question is what? That suppose that Q1, Q2, Q3 is 1. So it means that we have such kind of resonance condition. And suppose that these Q are generic. They satisfy this condition. But in a submanifold of Q's which satisfy this is a generic point. Is it true that in this case, this subalgebra there is generated by A1? And unfortunately, this is also unknown. No, maybe some simple algebraic consideration can help. But this I don't know. Now about suppose I have shuffled algebra and lambda is such functions, and I'm asking about quadratic relation. Algebra is A0 plus A1 plus A2 plus so on. To write relation, it is easier if no, A1 is a Algorand polynomial in the inverse, yes, and let me denote the I by EI. Yes, and the question is what kind of quadratic relation we have, and such quadratic relation can be written by the following way. One way to do it is following. Let me use some notation. That suppose EZ, maybe EZ is okay. It's the sum of the I, Z minus I. Yes, in such, it is just generating series, and it will be some confusion, maybe to avoid confusion, let us put some T's. Yes, and the quadratic relation can be written in generating function by the following: Et1 times Et2, and here I can write in, let me see, maybe lambda inverse. No, up to Kyoto Univ it will be correct. It may be some mistake, but T1 minus T1 T2, T1 minus T2 T2, T1 minus Q3 T2 is equal opposite. If T2 times T1. Here we have T2 and here minus T2 minus T1, T1, T2 minus T2, T1, and T2 minus Q3, one, it is a quadratic relation looking like this. No, first of all, what does it mean? And it means that quadratic relations are looking by the following. That this object is some polynomial, and this is some polynomial. And if you write down that E is this, then the structure of this relation will be the following. That you get E I plus 3 times Bj for some Bj. The coefficient I don't want to write now. That E I plus 2 E the sum J plus 2, yes. Then plus this also the coefficient will be coefficient of this polynomial actually. That it will be the sum of 4 terms. Then it will be E I plus 1 times E J plus 2 plus E I E J plus 3. And here we'll have opposite. E J plus 3 E I plus similar sum. Now, what I did, I just write down that E is a sum and write what does it mean. And we get, as a result, we get some relation and now I can formulate the problem for students if somebody wants to do it. First of all, check is this correct or not. Mistake can be in a place that I can change T1 and T2. So if possible. Therefore, check is this correct or not. It is correct up to this. And second, and second, it is all, and the structure of quadratic relation is just this. Yes, and by the way, what does it mean that if now also theorem this theorem says the following. Suppose again we are still working not in our situation, but suppose that Q1, Q2, and Q3 are generic. And theorem says that in this case, shuffle algebra, previous theorem said that in this case, shuffle algebra is generated by EI, but the additional thing is defining relations are quadratic. And just this. one thing about this. Suppose you know that in an algebra is generated by EI, but it has such kind of quadratic relation, which was such relation I wrote here. Then now, if you know quadratic relation, that in principle you can say something about size of the algebra, because no size it's not so easy, but at least what we can do. So our relations says that if algebra is commutative, it means that if you have EI in EJ, that this is the same as EJ in EI. In more complicated cases, we can, if we have some quadratic algebra which has the same size as algebra of polynomials in EI, we can find in an algebra just what people call it, the Grosvenor basis or things like that, the ordered monomial which gives us some candidate for the basis in the algebra. And you see, in our case, EI plus 3 EJ and EJ plus 3 EI is some kind of relation we have. Therefore, in our algebra, we have candidate for basis. And this candidate is looking like this. We can start with EI. Suppose I is this. Then who will be the next? Next, if we have EI and EI, if we have this times this, 1, 2, 3. If we have this product to this, then we have rewrite in the opposite order using relation. Therefore, in our algebra is the following candidate of the basis. I have first element EI. Then I have EI minus, in this direction, minus 2 plus something. Now EI1, left, right, EI2, EI3, and so on. That's such that I2 is bigger than I1 minus 2. I3 is bigger than I2 minus 2, and so on. So, element, this element, next can be something from this, and if it can be, for example, this. Next can be this or bigger. Next can be this or bigger, and so on. And so, no, from quadratic relation, we definitely know, if you believe in my quadratic relation, that surely you can rewrite the element and express any element from the algebra through this kind of basis. Yes, and but as usual in Grosvenor basis things, you need some additional arguments to say that it will be really the basis. And no, it is not evident, and it is not our subject, but nevertheless, just formulate it as I want. That I can prove that for generic Q1, Q2, Q3, such monomial give us a basis in the algebra. Okay, and so now we more or less understand how big this algebra is and what else that I do not know, well, but the description of the algebra is what? is polynomial in one variable, then polynomial in two variables. In three variables and so on. And this structure, we need too much to explain. This structure in some correspondence with this structure of the basis. You have these two here. And these two related with the fact that in the basis I shift by two the element of the basis. No, that no, well, the statement is that if you want to count by a natural way the rational function, the symmetric rational function, which has a pool of such type of the diagonal, that combinatorially, if you do it, you have to work with the same problem. And the basis in this space, natural basis in this space, without any Q, without any shuffled algebra, has the same structure. It is one thing, maybe it will be more clear later. But next statement. Well, now we more or less understand what is happening for generic Q1, Q2, Q3 in some sense. But algebra generated by this first part in existence of this resonant condition have to be smaller. It means the following things, that again, suppose Q1, Q2, Q3 is 1, but otherwise Q1, Q2, Q3 are generic. In this case, corresponding algebra, which is subalgebra generated by EI, what kind of relations here? First, quadratic relation. The same what I presented there, but plus cubic relation. Yes, and these cubic relations I will explain in a moment, and first example of cubic relation. Now this algebra, it has a rather remarkable property. And this property is following, that, well, I have generators. E0, E1, E-1, E2, E-2, and so on. Then I can write down, because this is also the, let me call it not theorem, but proposition. The difference is that what I call proposition, maybe later, a little bit later, maybe even today, I'll explain how to prove it. But first of all, what it claims? It claims that in this algebra, bracket E minus 1, E1, commute with this U. later we will see even more, but and what I write here, this one, this is example of cubic relation. It cannot follow from quadratic relation, which I wrote it as something new. And it is really depends on the fact that Q1 times Q2 times Q3 is 1. How to see other cubic relation? That shuffle algebra has, no, it is, this algebra is so simple that shuffle algebra has a rather big group of symmetry, or infinitesimal symmetry. Then it concerning any shuffle algebra. Suppose we have a shuffle algebra with some function lambda z1, z2, and does not matter even what function it is. Then it's much more general, but in our case, suppose that an algebra generates by just the inverse. Yes, and so it is algebra is A0 plus B1 plus B2 plus so on. Then on this shuffle algebra, we have big commutative Lie algebra is F. Yes, and in this case, the action is following. This Lie algebra is infinite dimensional Lie algebra. It has the basis Hi. I belong to C, and Hi acting on a space An by following simple way. Hi acting on a function f one so on n is equal f one n times the sum of the alpha over I. So this is just product to a symmetric Newton polynomial, and it gives us the symmetry, the infinitesimal symmetry of the algebra. And so it means that, for example, such, no, and this is completely evident from the formula for the product, here no problems. And it means that, for example, in this case, such Hi, if I apply it to generator for Bg, it gives me Bi plus G. Yes, and well, and surely if this is cubic relation, and if this algebra has such symmetries, so I can construct new cubic relation by acting, say, by H1 to this. I can, because this is 0, I can act by H1 to this, and write what does it mean. And it gives me what? It gives me, for example, in this case, E0, E1, plus e minus 1, e2, e0, and plus third term, e minus 1, e1, and e1 again. And this is also 0. And so I can produce a lot of cubic relations by this way. No, surely I can repeat this. I can take h1 again, then apply h minus 2, and get a lot of cubic relations. And here, our statement, what I was, that this algebra defining relation are quadratic and cubic. Quadratic, I said before, cubic, it does this. But if you want to ask about the cubic relations are describing, yes, but a little bit indirectly. I took some relation, which I claim is correct, and then start to act by symmetries and get a new relation. But it's a natural question how many the minimal choice of this cubic relation, and I want also to formulate this here, point 3, that the algebra shuffle is great. But it has at least two gradings. One grading is like this, A0, A1, A2, and so on. But it also has grading that degree EI equal I. And from this point of view, relation can be homogeneous. And, for example, relation E minus 1, E1, E0, the degree of this relation is 0. And my statement is that here, that the minimal choice of cubic relation we need two relations in each degree. So it means, for example, in degree 0, we have this relation and one more. In degree 1, we have also two relations. In degree 3, we have two relations. In all degree, we have two relations. And so, what I explained, that shuffle algebra has two relations, quadratic relations, and also cubic relations of such sort. Now, one question is how much familiar is the situation with generators and relations, and do we know some other algebras which such structure of relations? And the fact, the answer is yes, and this is what I explained, maybe 54 hours ago in the same place. Yes, and I determined in the end of my previous lecture the algebra, Lie algebra of Hamiltonian vector fields on a torus. And what I want to explain and wanted to explain, but maybe do it now, that actually in some sense it is a rather close object. Well, but let me recall what is it. So we had C star times C star. Function of C star times C star is, well, polynomial in P inverse Q inverse. So we have such notation. And Poisson structure here is very simple. It was PQ d over Q. Yes, and let me not to repeat the structure, but no, well, it is not very complicated. That Pi Qg. So we have the algebra with the base Pi Qg. So basis is labeled by two-dimensional vectors. And so we have Pi Qg, Pi prime, Qg prime. And according to this, it is what? It is P I plus I prime, Q J plus J prime. And here we have I J prime minus J prime like this. It is the algebra. Rather just simple, rather simple. The algebra with the same basis, and so I draw the letters. Well, and what actually we have in my algebra? First of all, we have C Q inverse, which no, it's important, but maybe I will not use it. But we also have what? So it was origin here. It was Q squared Q inverse. Well, here I have C Q inverse times P. It is here. Then I have C Q inverse times P squared and so on. Well, and now in this algebra, I want to restrict myself only this subalgebra of my Lie algebra. So where power of P appear, this power is bigger than C. Now, first of all, this Lie algebra generated by this part, and let Ei be equal Qi power P. Then in this Lie algebra, we definitely have quadratic relations, and these quadratic relations were what? That no, the object which I want to compare with my shuffled algebra is universal enveloping of this n. The n will be nilpotent subalgebra of this or just this. Nilpotent is notation for this Lie algebra, and so EI are generated. Well, and now what we have? We have EI EG is equal, I think, J minus I to some element F, that notation, but Fi plus G. Fi plus G is up to sign is what is Q I plus G times T squared. No, it is evident from, so it means that a quadratic relation in my algebra is just what gives me this. So it means that quadratic relations cause that the EI, EG is equal to I prime EG prime. If I plus G equals I prime plus G. So they are quadratic relation, and so it is fine. Yes, and now the problem for students is just abbreviation for something which is possible to calculate with more complicated application or less complication. But anyway, problem for students will be the following. Suppose we have Lie algebra generated by some symbol AI. I belongs to C. And suppose that defining relations are quadratic and just this. So we, as a result, we get some Lie algebra generated by I, which and this EI just subject of some quadratic relations, and we also can ask ourselves what size of this algebra will be, what basis in this. And we can ask about the algebra, and we can ask about universal enveloping algebra also. And for me, universal enveloping algebra is more important, but it is surely interesting for Lie algebras also. Anyway, we have two facts. That in universal enveloping algebra of this Lie algebra, A basis is given just the same monomials which I described here when talked about the this shuffle algebra for generic Q1, Q2, Q3. So what is the situation? I said that for generic Q1, Q2, Q3, this algebra, shuffle algebra satisfy some quadratic relation. And looking to this quadratic relation, in principle, we can conjecture later, we'll probably prove that such monomials, which I explained here, give the basis here actually the same story, but for Lie algebra now. But in the corresponding universal developing algebra, a quadratic relation which I impose here gives us the same structure of the space. So it means that the basis here will be precisely the same. And by the way, even in this case, no, it is not complicated. A little bit more complicated is the fact that which maybe I do not know a precise answer, but suppose you are interested not in universal developing, but Lie algebra. And in the Lie algebra, you can ask, no, about Lie algebra what? We have quadratic relation. Well, so what does it mean? I have EI. Fine. Quadratic relation means that quadratic relation are homogeneous. So it means that correspondingly algebra, this is the part in degree 1. In degree 2, we will have all brackets, and these brackets are this F. And so in degree 2 I have, so in degree 1 I have this, in degree 2 I have this, 0, 1, minus 1, and so on. Well, in our real algebra, which we are talking about now, I mean this Hamiltonian algebra, in degree 3 we have object like C, Q, Q inverse, we have PQ in degree 3. So it means in our real algebra, here we have also one element in each bracket. But suppose we do not talking about this algebra, but suppose we have just algebra with quadratic relation, and we can ask what we get here, just from Jacobi identity. We can use, I can calculate brackets, I can use quadratic relation and Jacobi identity, and the question how many elements I get here. It is simple calculation. This, at least for this, it is also for students, and you can easily find that in each degree only 3 elements survive. And so, for example, here I will have bracket this with this, but 2 more elements. And you can continue this and just ask how many elements we get here. And if you're asking about the answer is the dimension in each place of this algebra with such quadratic relation is the number of some trees in some program. And I'm not sure that it is really known. Maybe it is known to some people. I never use the correct answer, but it is something like this. Anyway, but if you're just talking about what is happening here, this is just 5 or 10 minutes calculation, and you immediately see that it will be this. And by the way, no, you can, no reason to do it just immediately. You can believe me, at least this is it. And well, and the fact is the following. Okay, but this happening in the algebra when we have only quadratic relation. But in our real algebra, in each place here we have only 1 element. Therefore, we need 2 extra relations to kill elements which we do not like. Therefore, in this algebra, which we have here, we have quadratic relation and two cubic relations in each degree. Yes, and this is easy to check, and even after this, it is not big problem, just some calculation that actually for this Lie algebra, defining relation just quadratic and cubic, like in our shuffle algebra. Not so much time, it's not good to start something new. So let me say one more, a little bit more, but well, you see that again, naively we can see what is going on. That on the level of shuffle algebra, if we consider Q1, Q2, Q3 generic, then if you believe me about the only quadratic relation, then for Q1, Q2, Q3 generic, no will condition, nothing like that, and it means that in the cubic part we have things like this. And but if Q1, Q2, Q3 equal 1, then I explain that this part becomes smaller. Smaller because of two will condition. And two will condition, it means that in this case, this space becomes smaller, and smaller by half. It is 0 on two diagonals. The 2 over C1 equal Q1, and the 3 over the 2 equal Q2. And also we can replace Q1, Q2. So it's smaller in each degree by two elements. Because function on the diagonal, they graded. Function on this shifted diagonal are graded by integers, and so algebra becomes smaller in each degree by two elements. And this is in a correspondence with the fact that we have two cubic relations. And so by this way, all this looks understandable. And now, one thing which I had in mind in my previous lecture, well, we have this shuffle algebra, and we have this universal enveloping of this Lie algebra, and they look similar, at least from the point of view of generators and relations. If yes, then we expect to have some flat family of algebra, which in some special point is universal enveloping of this, and in generic point is just shuffle algebra Q1, Q2, Q6. Yes, and and it is true, it is possible to do, but a little bit easier to do the following. Let us consider not also torus, and we can take now not algebra of the Hamiltonian vector fields on a torus, but a sort of quantization of this, which people calling quantum torus. It means that function on quantum torus is some algebras, let us put capital P and capital Q here, and no, and also P inverse, Q inverse, yes, and but it is non-commutative algebra. Relations are PQ equal Q small, QP. Here is Q completely different from that. Q is parameter. Yes, and by this way you get some associative algebra. And by the way, this associative algebra is just algebra of difference operators on a line. Because one Q is the product. No, this algebra is acting in function in Q inverse. Q is acting by product Q and P is acting by sheet. Yes. And then we can take, so anyway, this is associative algebra. And I can make up from this associative algebra Lie algebra with operator AB minus BA. Yes, and in this case, it is not a big surprise that this object is not far from this. And in some sense, yes, it is not far. And we can, but especially if we ask the same question. Well, so this is Lie algebra now, and it has commutative subalgebra, C, Q inverse, like this. And it has C, Q inverse P, and it has C, Q inverse P square, and so on. And the same question. We can consider this Lie algebra, and again, in this Lie algebra, the question about generators and relations, and yes, and let us do the same thing. So Pi now will be Qi times P, and if we calculate Pi in J, so what it will be? It will be, no, even in general it is simple, but we have Qi and we have QJP, and so it will be Q small G minus Q small I, and here it will be Qi plus J times P squared. Yes, again, I can confuse I and J, but up to this, it is correct. Yes, and then in such algebra, we have now quadratic relations, which are just the same, but we have to put here Qi minus Qj, and put here Qi prime minus Qj prime. Yes, and no, and you can easily guess that I want to say that here the structure is completely the same. So again, we have quadratic relation, we have two cubic relations in each degree, and they will be defining relations in my algebra. Yes. By the way, and it is closer to shuffle algebra in the sense that it is easier to say how to proceed. That I have shuffle algebra, and it depends in Q1, Q2, Q3. And if I take some parameters Q2 and send it to 1, then first of all, naively, shuffle function becomes symmetric, because here we have Z1 minus Z2, and it is transferred to Z1 here, and Q1, Q2, Q3 is 1, so we have this and this, and totally we have symmetric function in the limit. So algebras degenerate to commutative function. In such situation, we can do, if we have a family of algebras, we degenerate to commutative algebra, we can examine this situation by two different ways. One way, we can, this is degeneration to commutative algebra, so we can study the Poisson structure. And it is an interesting question, surely. Or we can do differently. Because our algebra for generic 1 to 2 Q3 satisfying this generate by EI and such EI, as I said, satisfying quadratic and cubic relation, then we can make up a limit in the relations. So just write down relations between EI, and then in this relation make up limit when this Q2 go to 1. Then a relation will go to some relation, also quadratic and cubic, and they just satisfy, coincide with quadratic and cubic relation for this algebra. So I have universal enveloping of this real algebra, which is starting with this. And as I said, this algebra satisfying quadratic and cubic relation, and we can get quadratic and cubic relation just by some such limit. And by the way, about cubic relation, I will say more a little bit, but checking about quadratic relation, it is very handleable things. You can take them, send Q, and look what is going on. Anyway, if you have family of algebra, it is a situation which is happening in many cases. And sometimes it's looking not very easy, but you see that, and they even produce some surprise. You have family of algebra, you take parameters, these parameters are going somewhere, and you are looking what kind of limit you can get there. Now, the experience, human experience, says us that in principle, a lot of in interesting situation, you can do it by many ways. And this, in quantum group business, it is standard. Yes. Now, okay. Now it is maybe time to stop.